So, what I have here is where we'll stop for test 2. There's a little more of this chapter on equilibrium. We'll do that for test 3. And really, this calculation using delta H, that's what I did at the end of class last time. But I have to cover these and I have to cover the energy diagrams. And most of this is not calculation. It's kind of conceptual stuff about energy. This other stuff in this chapter. I will call your attention first to this little set of facts. Breaking bonds always requires input of energy. In bond formation, it's breaking energy. When bonds are broken. But let me say this. We have our reactants, products, chemical reaction. So the reactants is where bonds break. Like if I have that and that molecule plus that molecule, and it makes H2O and CO2. The bonds that are being broken are all these bonds. All those atoms come apart, and then they come together to make these. So bonds are broken here in the reactants. Energy has to go in to break all of those. And then when they form, energy comes out. So that's really what that's referring to. I'll say this, but it'll make more sense when I go forward. It says when energy is absorbed, what I just described here, energy is absorbed. And then over here, energy is released, but it's not the same amount of energy. Sometimes lots of energy goes in here and only a little energy comes out here, meaning some energy stays in there. And that's when it would be this example. When energy stays in there, that's what this means by energy absorbed. It means overall, energy goes in, some energy comes out. If not all the energy that went in comes out, then some of it stayed in there, and that's what it means by absorbed. And that's when we say it's endothermic. The delta H value that I introduced in class last time will be positive in that case. That'll make more sense in a few minutes. So that's really just kind of a mention. Energy is released and it's exothermic, and the delta H is negative. But let's focus on, rather than that right now, the idea of bonds breaking and bonds forming. This chart here, if you needed it for the test, I'd give it to you. You don't need to memorize it. But notice the value, the delta H there is a delta H for, like if you just had a process that went like this. We have just H2, and then a reaction occurs, and we end up with H with its electron plus H with its electron. That's referred to as dissociation, and that's why we call these bond dissociation energies. For just H2, it takes 104 kilocalories per mole of H2 to break this bond. So that's how much energy has to go in to break this bond apart. The definition of a chemical reaction means bonds are broken and new bonds are formed. Both of those things have to happen for it to be called a chemical reaction. A chemical reaction is a process, it's a specific type of process, a chemical process, whereby bonds are broken and new bonds are formed. Here, a bond is broken, but no new bonds are formed. This is a process, but it's not a chemical reaction. It's referred to as dissociation. So this is really half of a chemical reaction, really. These have to go somewhere else and form new bonds for it to be an actual chemical reaction. But in this case, it takes 104 kilojoules per mole to break a whole mole of molecules of this apart like this. It takes 104. That would be, takes 104, I'll put the positive sign on there. You have to put that much in, and the positive means from the standpoint of the molecule or atoms. The amount of energy that's in here versus the amount of energy that's in this box with both of those. The energy in here has gone up by 104, meaning if this was sitting there at 100 units of energy, that means over here, if in this box it's sitting there with 100 units of energy, and over here we've got 204, it's gone up positive by 104. Whenever you use a delta, any delta for anything equals final minus initial. So this is the final state, and this is the initial state. So 204, that's the delta for this process that we're looking at. You see what I'm saying? Delta for anything is always final minus initial. If you went up to the square with 20 bucks in your pocket and you came back with 10, you went down by 5 bucks. Did I say 20? So you went down by $10. Your delta is negative 10. The two numbers involved in that was a 10, no, what did I say, 20? There was a 20 that you went to the square with, and you came back with 10. And you know that you're down $10. It makes total sense that your delta is negative 10. You can't get negative 10 by subtracting 10 from 20, but you can get negative 10 by subtracting 20 from 10. That's your delta. This was your final, and that was your initial. Your initial was $20, but you came back finally with $10. Other way around, if you went up to the square with $20 and came back with $30, it would be perfectly natural for you to go, I'm plus $10 when I came back. The process that occurred on the square, I'm plus $10. You went up there and sold me a watch or something. Final minus initial equals positive 10. The delta is positive 10. So it's always final minus initial, no matter what it is. If you start at a higher level and you go to a lower level, it's natural to think that your delta is negative. If you go from a lower level to a higher level, it's totally natural to think that your delta is positive. So it's always final minus initial. And the result of final minus initial is intuitively what you would expect it to be.
How do you get your final initial?
I just made those up.
Okay, you're just given.
I was trying to explain what delta means. You mean for this?
Yes, like how did you?
I just made up this,
Okay,
and because I know it's supposed to be 104, I just put 204 here so it would result in 104.
okay,
This isn't really how we measure these energy changes though. I'll come back to that in a minute.
okay.
We don't usually know the initial and final. What we do is measure the process, but I'll explain that.
So we don't, like, would you give us those numbers and we'd have to find it, or we'd have to find those numbers on our own?
I'll give you that chart and that's all you need, but you won't need stuff like this and it'll be obvious later.
Okay.
Uh, Two different ways. You go up to the square with $30 and you come back with, let's say you come back with $40. There's two different ways I could figure out your delta. I could stand at the edge of campus as you're walking out and search your pockets and what did I say, $30? Yeah, I said 30, right? I can't keep it straight. And I search you and I find that you have $30. And I give it back to you and you go to the square, I don't know what you do up there. And you come back and I stop you and I search you and I go, oh, you got $40 now. So I've made the two measurements and now I can do the subtraction, initial and final. Actually, the way we measure this, it's picture you pass me, I don't search you, but I follow you up to the square and I watch everything you do. And you make some transaction where you get $10 and I measure that. And then you're headed back to campus and I go, okay, so you can measure an initial and a final and then do a subtraction, or you can measure the process as it happens. But notice, if you go up to the square and I don't search you on the way, but I know you got $10 while you were there and you came back, I really don't know what your initial and final was. You could have had $100 and come back with 110. I have no idea what your initial and final was. I just know your delta was plus 10. So there are actually two different ways to figure out a delta. You can know the initial and final, or you can measure the process and never know the initial and final. It's that measuring the process that the way we actually do this. But I think I can make that more obvious later. All right, and let me just do this for the sake of being complete. What if I had that and made that? Well, this is a process, not a chemical reaction, but this is, I guess you could say this was reassociation, but we would really say this is bond formation. But this delta H equals a negative 1. When bonds form, energy comes out. When bonds break, energy goes in. You gotta put energy in to break the bond. That's intuitive. This isn't quite as intuitive, but it's just the inverse of this. When bonds form, energy comes out. So in this box versus what's in this box, energy has gone down, these two hydrogens, when they come together, lose 104 in the process. That's why this says negative. It's from the standpoint of the atoms or molecules themselves, not from the standpoint of the observer on the outside. Okay, so that point's worth making. Like I said, you won't have to memorize these. If you need them for the test, I'll give them to you. Another thing I can say here is, I'm not going to deal with that heat again. It is hot here, right? Okay, what's next? Oh, another thing worth saying is the more energy that it takes to break the bond, qualitatively we say that's a strong bond. Like this bond, the H to H bond, versus this bond, the iodine to iodine. This is a stronger bond than this because this is a higher value. The more energy it takes to break a bond makes it a stronger bond. So we use the word stronger and weaker qualitatively. Quantitatively, it's those numbers. Just trying to make sure to hit all the vocabulary. Stronger the bond, the higher the dissociation energy. I like this table too, table 6.3. This summarizes, I think it summarizes everything I already said. And all of these are like that. It's always two sides of a coin. It's either heat is absorbed or heat is released. Or delta H is positive, delta H is negative. When heat is absorbed, and when I say absorbed, I'll come back to that in a second. So all these bonds broken in the reactants are stronger than the bonds formed. Okay. All right, now it's time to do this. I'm going to work with this reaction. And I'm drawing out the molecules, but if I wrote these this way, CH4O, the formula for this, plus O2, the formula for this, H2O, plus CO2. All right, so instead of using the actual structure, I'm doing it formula the way we usually do these. And balanced, this equation is, so here's the balanced equation. I need 2 of those, 3 of those, 4 of those, and 2 of those. So that balances it. And let me do it like this. We have 2 of these, so I'm going to do this. I'm going to draw 2 of them. O, H. I need 3 of these. I need 4 of these. And I need 2 of the CO2s. C. So I'm going to diagram it out like this. And you can just use this chart. Let me bring that chart back up. There's a couple things here that aren't on the chart. The double bonds. O to O double bonds are not on there. C to O double bonds are not on there. They just have all the single bonds. But I looked those up before class. But here's the thing. Looking at the way this is, watch me count these. There's 1, 2, 3, 4, 5, 6 C to H bonds there. Can you see that? All right. There's also 1 C to O bond, single bond here. 1, 2, 3, 4, 5, 6. So 6 of those. C to O. There's 2 C to O bonds there and there. And then there's an O to H bond, so there's 2 of those. O to H. Here we've got 3 O to O double bonds. The values on this chart will be different. Well, they don't have double bonds on the chart, but bonds, a single O to O bond is different from a double O to O bond. So you have to find the double bond in a bigger chart somewhere. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 O to H bonds. You see that? And we have 1, 2, 3, 4 O to C double bonds. So now we can do this. You see C to H up here? Oh, we'll have to look at more of these. Why wouldn't they put them all here? Oh, I better say calorie, because they're gonna put it in joules. That's a very limited chart. That's in kcal, all right. this is what we want. And these are kilocalorie. Okay. C to O. There it is. 85.5. C to O. 85.5. C to H is, anybody see it? Usually these are alphabetical. Anybody see C to H?
It's
There.
H to C.
Yeah, but it's the same thing, so yeah, 99. O to H. You see it?
Go down to HC. 111. 111.
It's 111. Yeah, y'all just find it for me.
Okay.
111. O to O double bond. That was over here. 119. O to H we already found. O to C double bond was right around here. Let's just use, you can break these down to more specific situations. Y'all study aldehydes, ketones, esters, amides next semester. Let's just pick one. They're all about the same. Let's go with 178. Okay, and it shouldn't surprise you that I have to multiply this by 6 for those 6 bonds to find out how much energy it takes to break those 6 bonds. See what I'm saying? Do this in a spreadsheet. So this will clarify what exothermic and endothermic means. I just wanted to take y'all through the process. C to H. O to H. O, C. All right, there's 6 of those. It's 99. There's 2 of those. 85.5 of H. 2 of those. It's 3. It's 15. O to H. It's 8. 11. Now I'm going to go this times that equals this times this. All right, there we go. So I've added up I've done 6 times 99, 2 times 85.5, 2 times 111, 3 times 119, and then I summed them all up. And it says it takes 1,344 kilocalories per mole to break all these bonds. Makes sense? And then when the bonds come together, this is how much energy comes out. I've multiplied these up, added them up, that's how much energy comes out. This is initial, this is final. We want to do final minus initial. 1,600 minus initial. And equals this minus this, 256. That means delta H equals positive 256.
If you were just going to define one of those, like how much energy gets released, would you just do like the initial, so the, like say we did the first one, 6 times 99, and we got 594, would you just do that minus 100, or minus 99
That minus 99.
to get the energy released?
No, when you do this, you have to put, 1344, you have to put 1344 in, but you can't direct which molecules they go to. So you've got a reaction chamber that's got all this in it, and you're gonna have to put this much energy in to break all those bonds.
Okay. No.
I think what you're asking, I don't know what would be the utility.
I wasn't paying attention to the
Yeah.
part.
So that's how much energy goes in, and this is how much energy comes out. You get more energy than you put in. That's why it's exothermic. All right, so it's however much energy goes in versus how much energy comes out. You do the math, and this either comes out positive or negative. If it's positive, that means energy came out. Like I had a reaction vessel here and I have a reaction vessel here. I pour them together and you'll feel heat because energy came out. If I did one that's endothermic, you'd pour them together and you'd literally feel them and they'd be cold. I mean, you know, the beaker you're holding would literally feel cold to your hand. That would be endothermic. Okay, having said that, I'm not gonna leave all this here, I need to draw something. There's a way we can diagram this. And I'm missing stronger, higher, what was it? Oh yeah, I was down here, wasn't I? Okay. Let me draw this diagram. Let me say this. If you took the strength of all the bonds here versus the strength of all the bonds here, you can say that the bonds here are stronger than the bonds here because breaking all of these bonds took this much energy, but forming all of these bonds took that much energy. You see what I'm saying? This is telling you that the bonds and the reactants are weaker on the whole, all together as a bulk. They're all weaker on the whole than these. These were stronger. That's why energy came out. It is possible to have stronger here and weaker here. And then you don't get all the energy out that you put in. Anyway, so that's what this third statement is. If heat is absorbed, well, let me do this because that's what we've got here. If heat is released overall, considering reactants and products, if heat is released, we call it exothermic, the delta. Sixteen is final. It's positive. And I did do final minus initial, didn't I?
Yeah.
Makes me wanna double check these. Did I do these? I did C to O, I did O to H. Maybe it's not balanced. 2 carbons, 2 carbons. 8 hydrogens, 8. And 6, 7, 8. 4, 8. That's how much energy went in. That's how much energy came out. Final minus initial. What am I doing wrong? Energy comes out, it's exothermic. Well, let me draw this diagram. I can't stand here and think about it too much. I won't make you do that, do a calculation like I just did, where you have to estimate the delta H like I just did. Let me draw these diagrams, maybe they'll come to me what I did wrong. Oh, I know what I did. It's energy going in was positive 1344. Energy coming out that's what I didn't have this sign. These molecules lose 1600. These molecules gain 1600. So let's see if
Will the reactant always be negative then?
these are the reactants.
Or sorry, I meant the products.
The product, yeah.
Okay.
The reactants will always be positive because energy has to go in. That's what you're asking, right? And this will always be negative because energy comes out. Let's see if this actually works. Okay. That'll work. This might be confusing after my big discussion of final minus initial, but if you do it this way, I think it comes out right, because now we're ultimately going, now it'll be negative. So if you just add those two together, the positive value that you get for the reactants and the negative value that you get for the products, and you just add them together, then you get the negative whatever it was. 256, is that what it was? Yeah. Yeah. Final, never mind. Forget the final minus initial, so I don't waste time. I might have a brain part that big. Okay, so think of it like that. This much goes in, this much comes out. So it ends up being negative. I know my final minus initial discussion goes here, but I don't know what I've done wrong with it, so. So think of it like that, instead of my big final minus initial. Exothermic products are lower in energy than the reactants. Yeah, that makes sense. Okay. So let me do this. This is what we call the energy diagram. Get one down here. Theirs looks very busy compared to what I'm about to show you, but that's what I'm going to draw here. You've got an energy diagram. Here's the, and this is energy. Energy on this axis going up. And this is, I guess, we call this the reaction coordinate, but this just means the progress of the reaction starts with reactants and progresses and eventually becomes products. So right here would be the energy of the reactants. And right here on this scale is the energy of the products. And like I said before, we don't measure the initial and the final. When we actually do this in a lab, we measure the process. So in some sense, we don't even really know this. The difference between here and here, that's the delta H. So for the reaction I just did, there would be 256 energy units between here and here. You don't even need this hump to picture the delta H. But all reactions do this. They go up first and they go down. So this ramp up, that represents, here's another energy point. Okay, so that's energy, the vertical axis. That is energy. That's energy going in. In our case, this was energy going in was this. In our case here, energy going in, going up. And from here all the way down to here, I'll draw it over here. Say negative 1600. Does that make sense, what I outlined there? And that's what they're doing here. Delta H, okay. One more thing. We usually diagram that, this interval here, and we call it energy of activation. Activation energy, EA. So what they got here with an arrow is what I, for some reason, put over here. This is energy of activation. Activation energy. And what's the other vocabulary we want here? The transition state. This can't be taken too literal. But here's what I would say, in some sense, is the transition state for this reaction. Pretend there's two of those there, just so I don't have to sit here and draw all these. All right, there's the two reactants. And pretend there's 3 of those and 2 of those, like I had before. Sitting there like that, we're here on the energy scale. If I start breaking bonds, we go up to here, and by the time I get up here, you can pretend, this isn't strictly true, because it kind of also involves proximity of atoms to other atoms. But in some sense, 2 dots here, 2 dots here. This one's a draw these. Here they are with the bonds broken. And now that the bonds are broken, they could just like drift away from each other. So what I'm saying is, now I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 of those floating around. I have 2 of these looking things floating around. And I have 6 of these floating around. In some sense, all of that jumbled up, just hanging there, is what this is. That's the transition state. It's not strictly true because these don't usually just break up and hang around and then bump into each other. One of these has to get near one of these, and there's like an orientation and stuff to it. That fan fall over? Is there a ghost in here? I was walking around from vibrations. So the transition state is, just picture it as a point where all the bonds are broken and they're getting ready to start coming back together as the products. As they start to come together as the products, here they are losing energy, so there's energy going out, the exothermic form. So that's the energy diagram. Transition state. Okay, yeah. A couple other things to say about energy diagrams. This reaction that I did is happened to be an exothermic reaction. There are reactions, I won't go through this whole process again, but there are reactions that will look like this. An endothermic reaction, you start with your products, you're definitely going to go up, you always go up. You start lower. You always go up, and I should swoop this nice and smooth. But if it stopped like that, reactions to product, you see the difference? All the energy that went in, and here's the energy coming out, but not all the energy that went in came out. That's endothermic. This amount of energy is what's coming out here. It goes up, it goes down, and it crosses this point and goes down below it. Products end up lower than reactants. Here, products end up higher than reactants. So this is exothermic. This is endothermic. Endothermic. And notice now, going from here up to here, it's telling you delta H is positive. You see that on the diagram? So if you just saw the diagram and nothing was even labeled, you could look at this. And there's a lot you can tell just from looking at that. You could go, products are higher than reactants, so it's endothermic. You can say that these bonds are weaker than these bonds because it took this much energy to break bonds, but this is the energy that came out. So these were stronger bonds than these. What else can you say? Oh, all right. Let me hone in on. Here's the level where the reactants begin. Here's that transition state. Here's the energy of activation. Between there and there, the amount of energy you've got to put in to break all those bonds. Compare that with, I'll draw another endothermic reaction. I'll start here. Now, here's my energy of activation. Here's my endpoint. I tried to line these up straight across and these up straight across. So it's still the same delta H, but the difference is this took a lot of activation energy and this just took a little. So this would be a completely different reaction with somewhat weaker bonds in the reactants than these. It took a lot of energy to break up the bonds in the reactant here. It didn't take much energy to do it here. And if we compared this reaction to this reaction, we would say, just kind of a qualitative thing, we would say this reaction has a stronger tendency to occur than this reaction. Stronger tendency. Another way to say that is this reaction will go faster than this reaction at some particular temperature. So two more qualitative things you can look at. If you compared two things like this, you could say that, like I said, the reactants here are weaker bonds than the reactants here. And you can also say that this reaction has a stronger tendency to occur. And you could also say this reaction has a tendency to go faster than this reaction. That activation energy is sometimes referred to as the energy barrier. And if it has a low energy barrier, it has a stronger tendency to occur. And when it occurs, it will occur faster. I think that's all the qualitative stuff I need to say about energy diagrams. Favorable, not favorable. Another way to say it, this reaction is more favorable than this one because it has the lower energy of activation. It happens easier. Transition state. So in my pure idea of having all the atoms split apart up here and then they start forming here, it doesn't really happen like that. Another way you can say it is when you're here at this peak at the transition state, at the top of the activation energy, you can say, what was I thinking? You can say that the bonds in the reactants are partially broken and the bonds in the products are partially formed. It's sort of like the reactants don't all break apart all at once and then all become atoms and then all come together as products all at once. It's like some of the reactants have broken apart and some are in the process of breaking apart. They're going up here. And then those first ones that broke apart, they're beginning to find each other and start to make the product. So it's not like it all happens at once. It's gradual. Some reactant goes, starts becoming products. Some more reactants go and start becoming products. So some of, or not all, but probably most of the reactants, when you get here, the bonds are broken, but you just say they're partially broken. And the products are beginning to form up here. So reactants bonds are partially broken up here, and the products bonds are partially formed up here. It's another thing you could say about the transition state. The transition state is actually a very complicated thing, which is why I'm dancing all around it. But just those qualitative things are all you need to know. Transition states are something that are heavily researched because it's never really obvious. I mean, in a lab, generally you know what your reactants are. You can characterize that very easily and study it, and you can get your product and you can take your beaker and put it through instruments and measure it a lot. But the thing is happening as it's happening, that's a very difficult thing to measure. So it's the subject of a lot of research. Okay, I think that completes it. Let me go through. I do have, and I'll remind you, for test 2, it's this from chapter 4, it's this from chapter 5, and I've got these two that you'll see, And this one, reaction energy calculator, energy and reactions. Test two. We call that chapter 5. So I want to go through some example problems. Let me put chapter 6 on this. I'm usually in here before y'all get here. I should go open that door every day before y'all get here. That heat gets to me as soon as I start talking. I dread warm weather. I dread that humidity that's coming. I dread it every spring. All right, let's go through a few examples. Questions like this, is it endothermic or exothermic? When delta H is negative, I won't give you that chart. The one that keeps confusing me every time I look at it. Let me do something. Because I want y'all to be able to look at that chart. This. Awesome. Oh, I'll save that. What do? Say copy? Did that save it? Did not. I'm not good with that snip tool. I highlight it. Did that do it? There. So I won't give you this chart, just know it enough to answer questions like this. So I need, go back here. Three. But okay, now that we're situated, you can answer all of these. It's just a matter of knowing that chart. I gave you the logic and why the information in that chart is what it is. But if you just memorized that chart, if delta H is negative, is it exothermic or endothermic? Exothermic. If the energy of reactants is lower than the products, reactants are lower than products. Here's the reactant, it's lower than the products. So in the overall process, energy was absorbed. Some of the energy that went in stayed in there. So that would be endothermic. If the reactants are lower than the products. Reactants lower than the product. If energy is absorbed in the reaction, is that endothermic or exothermic? Endothermic. Bonds in the products are stronger than the bonds in the reactants. It's literally in that chart over there, everything I'm saying. So if you can learn that chart, it helps to know the logic and why the information in that chart is what it is. But if delta H is a positive value, is it endothermic or exothermic? Endo. So you see what I mean? Answering questions like this, it's just that chart. I won't give you that chart on the test, but it's as simple as knowing what's in that chart to answer these types of questions. All right. So 23 and 24 at the end of the chapter, 6.23 and 6.24. Some practice with those. 29. It might still be useful to have this chart. How do I really want that smaller, but I guess that doesn't help, does it? Too big. I always long for 2 projectors in a classroom. All right, whatever. Okay. Consider the energy diagram below. Which point of the graph corresponds to reactants? X, Y, or Z?
X.
The products, Z, the transition state. The difference in energy between which 2 points equals the energy of activation. And they're talking about on this axis now, X and Y. If you drew a line straight out here, and you drew a line straight out here, it's from the X to the Y, that's the energy of activation. It's from the energy of the reactants to the peak of the diagram. Difference in energy between which 2 points represents the delta H? X and Z. Here's where the reactants start, here's where the products land. If you drew a line straight out to the energy axis here, and drew a line from the energy axis out to here, it would be from there, X to Z. You guys see this? Which point is highest in energy? That should be very obvious. And it's always true for any reaction. It's right there at the peak of the transition. In this case, which point is the lowest energy? Z. They don't ask this, but is this endothermic or exothermic? It's exothermic. However much energy you put in, you lose more energy than you put in. So it's exothermic. I have 30 on here. Y'all can look at 30. They just diagrammed 2 reactions on the same. Still have 31. 31 and 32. We will all right. So if I'm going to draw an energy diagram, what does it want? Draw an energy diagram that's got a reaction that has a low energy of activation and the delta H is negative. Delta H negative means I've got reactants and products down here. Exothermic. And if I want to show low activation energy, I'm only going to go up to my peak just a little bit. Maybe I should do this. And then I'll go up just a little bit and then down. Energy. Delta H is negative. Yeah. So exothermic. So this really isn't a very good way to put it, because low with respect to But, so I made a little bump here, but really you would have to compare that to something to say whether low is too qualitative. A slow reaction in which the products are lower in energy than the reactants. Okay, a slow one, if we want it to go slower, we have to have a higher activation energy. So all I really need to do is make sure my products are below, be a little careful there. So I'm saying that's the delta H. Now this will go slower because it's got this higher energy barrier, higher energy of activation. So that's the answer to the second one. This one. Now do a slow reaction where the products are lower in energy than the reactants. So the only difference between this description and this description is that lower, smaller activation energy versus a higher activation energy. This one will be slower because it's got the higher activation energy. Less of a tendency to occur than A. Still exothermic, but it takes a lot of energy to get that reaction to go. A diagram that has a low activation energy, you can think of it like this. I've got two reactants and two beakers. I'm about to pour them together. I pour them together and they just immediately react. That means room temperature was plenty, just a little activation energy. The temperature it was at room temperature was plenty to make it happen. But if I pour them together and nothing happens, and then I have to put it on a hot plate and heat it up for a while, that's this situation. You've got to put some energy into it. You've got to really heat it up. Room temperature is not enough. In the lab, a lot of times we set up the hot plate and put stuff in. Those are high activation energy. I could do this next one. Maybe I will, but let me see what else I've got for the next 10 minutes. 32, 70. This is actually an equation I was using earlier. We'll do equilibrium stuff later. All right, let me do this instead. Let me just show you these. I put a bunch in here that are fill in the blank, but there's a fair amount here, but it just kind of covers all this information. It's kind of repetitive. When delta H is negative, the bonds formed in the products are blank, then the bonds broken in the reactants. What do you think that is? This one is stronger versus weaker. In a blank reaction, heat is absorbed. This is exothermic versus endothermic. Which one is that? Heat is blank in an exothermic reaction, released or absorbed. In a blank reaction, the products are lower in energy than the reactants. So that's going to be products lower than reactants is exothermic. So exothermic versus endothermic. Label C is, you would just put here transition state. What do you think this is? Formation of chemical bonds, aka bonds. Is that endothermic or exothermic? That was all the way back at the beginning of class, but think about the reactants. When you're breaking those bonds, is that endothermic or exothermic? Energy's going in, so that's endothermic. Energy going in is endothermic, energy coming out is exothermic. When you're just talking about bonds without a full reaction, when you're breaking bonds, energy's going in, so that's endothermic. When the bonds form, that's energy going out, exothermic. Did I say it wrong? Endothermic, when energy's going in, breaking bonds. When the bonds are being formed, energy's coming out. You put those two things together for a full chemical reaction. Energy goes in and energy comes out. And in the balance, then you decide whether the overall reaction is endothermic or exothermic. Oh, six I shouldn't have put in here. I need to delete that. I didn't say that, but have y'all heard the law of conservation of energy? I didn't say this in class, but energy can be neither created nor destroyed. Which bond is strongest? You look at that chart of bond dissociation enthalpies. Bond dissociation energies. It is called enthalpy, but this book doesn't use that word, so. Anyway, I think y'all can do these. Got a bunch of true false here. Bond breaking is endothermic. Is that true or false? It's true. Exothermic reactions involve the formation of products lower energy than reactants. That's true. All right. Y'all think y'all can do these? All right. That's it. So be sure and get to those. We'll review Tuesday. We'll have test 2 on Thursday. If you hadn't been doing these, get to them. We'll review Tuesday. So be ready with questions if you have them.